So this using this Dean-Stark dissolution adapter can continuously remove water from a reaction system by azeotropic distillation. And this basically can help you shift the Fischer acidification equilibrium to the right side. So the purpose of adding benzene or toluene is to bring the water of the reaction system, continuously bring the water in the reaction system out of the the reaction mixture. So shift the equilibrium to the right side. Okay. Now, in addition to reacting with carboxylic acid, alcohol can also react with other compounds that can donate, the called acyl group. So this whole thing called acyl group. Okay. So the carboxylic acid has an acyl group to donate. Okay. But in case of a carboxylic acid, when they react with alcohol, the reaction is an equilibrium reaction. But if you're using acyl chloride, this reaction is not reversible, especially when you carry out such a reaction in the presence of pyridine. And the pyridine is a base. And the details of this reaction we will talk about in a later chapter. But at this point, what you need to know is in the reaction, again, the alcohol serves as a neutral nucleophile. So in the ester product, entire this alkoxy group come from the alcohol, and the acyl chloride provides that acyl group, and the pyridine serves actually two purposes. One is a base because it can remove the formed hydrogen chloride, and the second thing is a catalyst. And you don't need to know by what principle pyridine can act as a catalyst. At this point, we will discuss in probably chapter 20. But the essential thing you need to know at this point is the alcohol serve as the nucleophile. So this alcohol attacking this carbonyl carbon eventually give you the ester. And if this alcohol has a chirality center, the chirality center will be completely retained in the ester product. Just say again, I'm gonna using when we talk about the chirality center, generally I would like to using a Fischer projection. So that's using I often use this structure because it's the simplest chiral alcohol. Say this one, right? It's a Fischer projection. If you react with pyridine, so what happens is just the alcohol, the chirality center in the alcohol structure will not change at all. So this structure completely retained in the ester product, and the rest of them of molecule is from the the acyl chloride. This one we call acyl chloride. Okay, so if you have a chlorine connect to carbonyl, the other side we have hydrocarbon. This is called acyl chloride, and obviously we know it from hydrogen chloride product. Hydrogen chloride going to be combined, will be absorbed by pyridine. And similarly, you also can have the acid anhydride to serve as the acyl group donor. So what we can see is one acid anhydride will donate one of the electrophilic acyl group combined with alcohol, give you the ester product, and the rest of the acid anhydride will be the cleaved off and become a carboxylic acid. So we can just again look at one example. So here, assume we have a cyclic acid anhydride. And again, we could using pyridine. Okay. So what happens again? You're gonna the alcohol will be serving as a nucleophile with the hydroxy group as attacking atom. So the alcohol part, vast majority of alcohol part structure will be retained in the ester, except the proton will be gone. Then this oxygen will be connect to one of the carbonyl carbon in the anhydride, and then the other carbonyl group in the anhydride will be exist in the form of carboxylic acid. Because of the cyclic one, so they will the molecule will be the carbonyl will be connect to the ester, give you the the product. Now, if you just have a regular acid anhydride, that will be a bit simpler. So again, because of the alcohol is a nucleophile, so the majority structure of the alcohol will be retained, except that the proton will be taken away, and the acyl group come from anhydride, then plus this is basically the left side provide it's electrophilic acyl group connect to the nucleophilic hydroxy oxygen, and the right side will be breaking off and give you the carboxylic acid. So these are the reaction, the kind of a few reactions where the alcohol serving as a nucleophile with the hydroxy oxygen as a nucleophilic attacking atom. And in the early part of this chapter, we have seen that carbonyl can be reduced into alcohols, either by catalytic hydrogenation or metal hydride reduction. So if carbonyl can be reduced into alcohol, so alcohol technically also could be oxidized, into carbonyl. So if we start with a primary alcohol, you actually may oxidize into a stage of aldehyde. But in most of cases, you will see that this formed aldehyde. Okay, if you oxidize a primary alcohol, you will go through a stage become aldehyde. But that aldehyde, in many cases, will be even easier to oxidize than the alcohol, and the aldehyde will be further oxidized into carboxylic acid. So how this reaction will work, we're gonna look at the mechanism. Okay, but the key feature is that if you have a primary alcohol, if the reaction system you use involve water, then the oxidation will go all the way to carboxylic acid. Okay. Now, if the reaction, if you have a primary alcohol, the reaction does not involve water at all, means basically is in a completely anhydrous condition, then the primary alcohol can be oxidized and stopped at the aldehyde stage. In the most commonly used situation, we are using chromic acid as the oxidant, and the chromic acid, you always using in aqueous solution form. In that case, if you start from primary alcohol, you treat it with chromic acid, then you will get the carboxylic acid as the oxidation product. And in a laboratory setting, we usually using a mixture of sodium or potassium dichromate and the sulfuric acid to to give us access to chromic acid. So this mixture, okay, is pretty much just a chromic acid mixture. And this also has a name called, I think, a Jones reagent. Okay, so if you treat a primary alcohol with a Jones reagent, then it will give you carboxylic acid. And if you have a secondary alcohol, it will always form ketones. Okay, and why we're gonna talk about later. Okay, when we talk about mechanism, you will understand why the secondary alcohol will not be further oxidized into carboxylic acid. And the tertiary alcohols, they generally do not react, or they form complicated mixtures under forcing conditions. So we don't really need to worry about tertiary alcohol react with under oxidation condition. So now, what if you want to oxidize a primary alcohol into aldehyde stage? And in that case, you have to use an oxidant that does not involve water at all. Okay, why? If you want to stop at aldehyde stage, you cannot involve water. We will revisit the reason in chapter 18. But for the time being, please just memorize for the time being. Okay, we will fully understand this in chapter 18. Why we need a completely anhydrous system if you want to oxidize the primary alcohol into aldehyde. Okay, so because we need a complete anhydrous system, so we usually cannot using chromic acid if you want to get the aldehyde from alcohol. So there's two commonly used, chromium 6 chemical species. The chromic acid, in chromic acid, chromium has an oxidation number of 6. So this is one of the highest oxidation number you can have on chromium. So that's why chromic acid is highly oxidative. And but the chromic acid is not soluble generally chromic acid is not soluble in organic solvent. So to make the, oxidative chromium 6 species soluble in organic solvents, so chemists develop two kind of oxidants. One's called pyridine chlorochromate, called PCC. The other one called pyridine dichromate, called PDC. But the common feature of those two oxidants is that both of them are chromium 6 species, an organified chromium 6 species. So those two guys can be soluble in organic solvent. So the most common used solvent for this kind of reaction is dichromethane. And the PCC and the PDC pretty much serve the same purpose. Basically, oxidize the hydroxy, the primary alcohol to aldehyde. And You also can, if you want to, you also can use the PCC or PDC to oxidize, secondary alcohol if you want to. Okay, PCC dichromethane, it will be do the same thing, oxidizing the, uh, the an alcohol into ketone, be it secondary or primary. Okay? So it's critically important if you want convert a primary alcohol to an aldehyde, you have to using an anhydrous organic solvent and use the either PCC or PDC as the oxidant. Now let's look at the mechanism. Now with that probably you will be able to understand why at least why how this reaction work, okay, and why partially you can understand why uh, the what call the ketone, the secondary alcohol, will not be further oxidized into carboxylic acid. Only the primary alcohol may be oxidized into the further oxidized into carboxylic acid. Okay. Anyway, when if you let's look at the reaction between an alcohol and a chromic acid. Okay, so when alcohol and chromic acid react, the first stage, the reaction, you can consider this chromic acid just behave in a very similar way as carboxylic acid. So basically these two things mix, the reaction is just like a Fischer acidification reaction. So the alcohol hydroxy group of alcohol serve as a nucleophilic atom attacking of the electrophilic chromium. So this gives you alkyl hydrogen chromate as the the kind of ester. Okay, this is the first step. This is equilibrium reaction. So it doesn't matter what kind of alcohol you have. Okay, even you have a tertiary alcohol, this reaction still happens. So let's see if you have a tertiary alcohol. This is the equilibrium reaction. Okay, the reaction still happens. However, if you have a tertiary alcohol, the reaction will stop at this stage. Okay, and this is equilibrium reaction. So you just have equilibrium mixture of the chromate and the alcohol. Now, if you have a secondary or primary alcohol, means that at least have one alpha hydrogen bound to the the carbon next to hydroxy group. So what happens this chromate, okay, will undergo E2 elimination reaction. So the water will act as a base, take this the proton away, and then this pair of electrons will come to the between this carbon and oxygen, become the pi component, and obviously this one gonna come to here, become a chromite ion. Okay, so this is E2 elimination reaction, and the E2 elimination reaction requires that this is a one, the at least one proton connect to this carbon. So in case of the tertiary alcohol, there's no proton connect to this carbon. Okay, so they cannot undergo further elimination reaction, so cannot form carbonyl group. But here, for secondary alcohol, after formation of alkyl hydrogen chromate, you do have a proton here, can be taken by the water. Okay, so under the This reaction is just like the E2 elimination reaction. I hope you recall the E2 elimination reaction. We have a learning organic 1. Just give you example. So in organic 1, you learn the dehydrohalogenation of of alkyl halide. Okay. So this is mechanistically this E2 elimination and that E2 elimination is no difference. Only difference just we are using a weaker base water to remove the proton from from this carbon. Okay, and the other difference is we are forming carbon oxygen double bond instead of carbon carbon double bond. But anyway, this give you aldehyde or ketone. Okay. Now the why the ketone will not be further oxidized, but aldehyde can be further oxidized, is because of the aldehyde. Okay. If it's aldehyde, okay, you still have one hydrogen bound to the carbonyl carbon. So this aldehyde, as we're going to see in chapter 18, will react with water, become diol, okay? React with water, okay? And then this diol can further react with another molecule of chromic acid, and keep more importantly in the form the chromate, the chromate, okay, it will be still one hydrogen on the carbon connect to oxygen. So that I can further undergo, the E2 elimination reaction, give you carboxylic acid. But if you have a ketone, okay, you no longer have a hydrogen connect to carbonyl carbon, so you will not be able to undergo further elimination reaction, even it react with the chromic acid. So that's why if you have a secondary alcohol, it oxidizes into ketone, will be stay there. But if you have primary alcohol, if you treat with chromic acid, it actually will go all the way to carboxylic acid, because of the primary alcohol first will be oxidized into aldehyde, then the aldehyde will react with water, give you a diol, and this diol can further be oxidized by chromic acid, okay, into carboxylic acid. Any questions about the oxidation of alcohols? So basically if you look at oxidation of alcohols, assume using chromic acid as an oxidation agent. The first step is the formation of the chromate. The second step is the elimination of the chromate, give you carbonyl compound. That's why tertiary alcohol, they do not react with chromic acid. And the secondary alcohol will give you ketone. And the primary alcohol, if you react with chromic acid, first will be oxidized into aldehyde, but then aldehyde will be further oxidized into carboxylic acid because of involvement of water. And if you want to oxidize, the primary alcohol into aldehyde, you have to use PCC, PDC, in dichromethane as a solvent. Okay. So that's just look at a few examples of the oxidation of alcohols. So what kind of product you will be getting from this oxidation reaction? You are getting aldehyde, ketone, or carboxylic acid. So the first step, this oxidation reaction overall always first, you are removing a molecule of hydrogen from the cross this CO bond. Okay, so you're getting this one. Okay, but because we have water there, so they eventually will become carboxylic acid. Then similar thing, but you have this one. What you will be getting? Okay, thank you, Mr. Hu. So this indeed is ketone. Okay. Now if we just give a slightly different example, okay, so you have a diol, okay? One is a tertiary alcohol. The other one is secondary alcohol. So what product you will be getting? So tertiary alcohol, okay, they generally don't react, okay, because of they just form equilibrium mixture, and the equilibrium constant usually not very high. So tertiary alcohol will be retained, okay, and then the secondary alcohol will be oxidized into the ketone. And let me see. And now in this case, okay, so the PCC is oxidant, so you will oxidize alcohol into its carbonyl form, both secondary and primary, okay. And the only difference is the primary one will be oxidized into aldehyde, and the secondary one will be oxidized into ketone. All right, so this is about oxidation of alcohols. Next thing we're gonna look at, the oxidation in the alcohol in biological system. So when we oxidize alcohol in test tubes, we can using chromic acid, but the chromic acid is such a powerful and actually too powerful to be extremely toxic for biological system. So the alcohols can also be oxidized into the aldehyde in biological system, and this actually is one of the one important reaction happens when when someone drinks alcohol, and alcohol will be oxidized into aldehyde first. Then, you know, the aldehyde will be oxidized, further oxidized into carboxylic acid. So if you drink ethanol, it will be oxidized into acetaldehyde, and acetaldehyde then will be further oxidized to carboxylic acid. So as I said, in the biological system, chromium-based oxidants are too strong and too toxic, and you know, but biological system had their own, you know, kind of you know, the oxidant is called, you know, the called nicotine amide. Okay, so basically the key feature is positive charged pyridine nitrogen atom, and somewhat, you know, the electron withdrawing carbonyl group on the ring. Okay, so this combination makes this you know, this kind of moiety you know, the mild oxidant. So so how does this thing, you know, this called NAD plus, okay, nicotine amide, okay, you know, how does this one perform the function of oxidized alcohol? So basically, because of this combination of positive charged nitrogen and electron withdrawing carbonyl group, NAD plus is you know, wants to be reduced. So you know, when it's carrying out, you know, the function as an oxidant, what does it just steals a hydride. Hydride means not only not taking the proton, you're taking the hydrogen together with a pair of electrons. Okay, so it steals, you know, a hydride, you know, from the carbon next to the hydroxy group, and this is also can be a kind of E2 elimination. So basically is the you know, the base steals the proton away, then the pair of electrons in the hydroxy group will be coming to here between carbon and oxygen, become the pi component, and then this you know, the whole hydride serve as a leaving group, leave the molecule. You know, this reaction, if without the presence of NAD plus, okay, will be a horrible, because you know, it will not really happen because hydride, okay, is a horrible leaving group. You know, you know, a leaving group quality is generally associated with its basicity. A more basic leaving group is a worse leaving group. Okay, and the hydride ion, okay, is exceedingly basic. Okay, so if in the absence of NAD plus, this elimination certainly will not be happening because hydride is such a horrible leaving group. Okay, but because NAD plus, you know, by the virtue of having a positive charged nitrogen atom, pyridine nitrogen atom, and the electron withdrawing carbonyl group, it's basically, you know, the very hungry for electrons. So the main driving force in this step is NAD plus want to steal a hydride to have have the molecule to be reduced. So combine because of the, you know, the thermodynamic driving force for NAD plus to want a hydride makes the whole E2 elimination reaction feasible. And then the E2 elimination reaction give you, you know, the acetaldehyde as a product. And certainly the other driving force come from the basicity of the base. So you know, so this again, you know, in a biological system, you have E2 elimination, and but the leaving of hydride, which is a horrible leaving group, is greatly facilitated by the willingness of NAD plus to steal a hydride to have this NAD plus reduced, called NADH. This is reduced form of the NAD. And this one, and as you're going to see later, actually also can serve as a reducing agent. All right, so the next reaction is kind of, we're not really going to the mechanism of this reaction. Instead, we will, treat this kind of reaction in a similar way as the ozonolysis reaction we learned in organic 1. And in this reaction, we treat a vicinodiol using, the HiO4 periodic, acid. Okay, so in this compound, iodine has oxidation number of +7. So this one is also is a oxidant, and the reaction mechanism is kind of interesting in a sense. Basically this when you have this HiO4, when it reacts with vicinodiol, it leads to the cleavage of the CC, the bond in the vicinodiol. So the reaction, you pretty much, and basically give you 2 carbonyl compounds. So this reaction can be understood in a similar way as the the ozonolysis. And if you recall, in the ozonolysis reaction in organic 1 is that if you have alkene, you treat with ozone, then a reducing agent. Let's say ozone, then a reducing agent. It could be a dimethyl sulfide or just zinc, water. Okay, but anyway, so this will give you 2 carbonyl compound. Just you cleave this bond, okay, give you the 2 carbonyl compound. And in case of the vicinodiol, the reaction pretty much, the same. Let's say vicinodiol often is prepared from alkene. And if you recall that, we basically need a peroxide, then osmium tetroxide, and it's not you can add them all together, OH minus, and this give you the vicinodiol. Then if you treat with HiO4, so you just cut the carbon-carbon bond, so you get the 2 carbonyl group. So this whole sequence of treating with using the the dihydroxylation and the treat with periodic acid, it's equivalent to just the ozonolysis reaction. Equivalent to, okay. So that's just one of ways, I think I would suggest you use to memorize this cleavage of vicinodiol. So just in pretty much the same way as ozonolysis. So if you have if you treat it with HiO4, you just cut here, okay. And then left side is a carbonyl compound, okay. Right side is another carbonyl compound. That's it, okay. And if it's a cyclic one, you just cleave the just cleave the carbon-carbon bond between 2 adjacent carbon atoms. And I just give you one more example. We just cleave here, okay? Don't cleave additional bonds. So this basically concludes all the reactions we will be learning about alcohols, but also we want to spend a bit time on thiols. As you can guess, thiols are the sulfur, counterparts of alcohols. So instead of OH functional group, we have SH functional group. And the structure and the reactivity, they are somewhat similar to alcohols, but there also there's some difference. Okay? So the one of the feature of thiols is their very offensive odor. Okay, thiols, odor is called legendary. Okay, if you unlucky enough need to deal with thiols, you probably wish your nose is not ultra sensitive. And actually this the horrible odor of thiols is actually is being utilized by the gas companies to facilitate users to detect potential leak of natural gas. So in the natural gas itself is odorless. So in the gas company, they basically added a methanethiol, this guy, okay, into the natural gas. So if you leak, okay, so the you will immediately smell it, okay. So if you smell natural gas, not because of natural gas, it has an intense odor. It's because of natural gas company purposely added a small amount of methanethiol into natural gas. Okay? So that makes a leak very easy to detect. Okay? Anyway, that's one of the interesting, the properties of the thiol. Okay? And although the structure of the thiol is pretty much similar to the the alcohols, there's some important difference in reactivity between thiols and alcohol. First thing is, the thiols, okay, they are much more acidic than alcohols. So I hope you recall alcohols, the pKa generally ballpark number pKa is about 16. Then depend on the exact structure, the value may vary, but the ballpark number of conventional alcohol is 16. But the pKa, okay, but if you take regular thiols, the pK is around 10 to 11. So that means the thiols is about 5 to 6 orders more magnitude, more 5 to 6 orders of magnitude more acidic than alcohol. That's a major reason because of the SH bond is substantially weaker than OH bond because S is bigger than O. So SH bond is longer, so weaker, so easier to break. Okay. And for this reason, the conjugate base of thiols we call thiolate. Okay, they are substantially weaker bases than alkoxides. And but thiolates, they are much better nucleophiles than the alkoxide. Why? We discussed in chapter 6, organic 1, mainly because of the electron pairs on the sulfur, they are much more polarizable than the electron pairs in on the alkoxide oxygen atom. And also you know, if you look at thiolate, they are, you know, the sulfur atom, nucleophilic sulfur atom is much bigger than nucleophilic oxygen atom. So, you know, this nucleophilic sulfur atom is substantially less solvated by solvent molecules compared to the oxygen atom in alkoxide. For these two reasons, thiolate is, you know, the about 100 times more nucleophilic than alkoxide. And that makes thiolate, you know, the excellent nucleophile. See, first is less basic. Second is more nucleophilic. So if you need to consider the competition between the E2 and SN2, you will see that thiolate will heavily prefer SN2 if you have a secondary, you know, the halide as an electrophile. If it's tertiary halide, even using thiolate, you will still have E2 as a major reaction because of the just, you know, the tertiary halides, SN2 just is so much blocked. Okay, so it's practically impossible to have SN2. Okay. Anyway, if you have a secondary halide combined with thiolate, you can have a SN2. And this just illustrated by this reaction. You have this 3-chloropentene. It's allylic and a secondary halide, and the combined with a thiolate as a nucleophile, you see the you get a SN2 product as a major product. And how do we know it's SN2? You see the configuration inversion. Okay. So the original the chloride is on the dash bond, now the nucleophile is in wedge bond. So you know it's a configuration inversion. It's a feature of SN2 reaction. And if you take this guy, treated with you know, the say alkoxide, okay, you will get eventually 100% elimination product. Okay, if you treat it with alkoxide. Why? Because, again, I hope you recall what you learned in Organic 1, Chapter 7, I believe. Okay, there's when you consider the competition between elimination and SN2, that we need a reference system. A reference system is a secondary alkyl halide and alkoxide. And that kind of system, you have E2 elimination as a major product. And here, this particular secondary halide even more likely to undergo elimination reaction. Why? Because if this guy undergo elimination reaction, you will get a conjugated dye. Okay, so the, you know, you basically further, you know, prefer elimination if using alkoxide as a nucleophile / base. But you using thiolate, the story is different. Okay, thiolate is excellent, you know, the nucleophile and a much weaker base. Keep in mind, if you want to undergo E2 elimination reaction, the nucleophile must act as a base to remove proton from the, you know, the electrophile. So here, you know, if you want a E2 reaction, okay, the base / nucleophile must take this one away, okay, then this off this one, okay. That's how the E2 work, okay. And the thiolate is a weaker base and a strong nucleophile. So weaker bases slow down E2 pathway. Stronger nucleophile speed up SN2 pathway. That's why when using thiolate with the secondary halide, you get a mostly, you know, SN2 product. So this is something I hope, you know, by reviewing this, you can get a bit more understanding, you know, on the aspect of elimination, substitution, competition. This is something very important in the Organic 1, and probably, you know, we also gonna see a few times in Organic 2 as well. Okay. Now, just like alcohol style, they can also be oxidized. Okay, but the oxidation oxidation product of thiols is actually quite different from the alcohols. In case alcohols, we know is that if you have say primary alcohol, okay, you oxidize depending on the what kind of system you use. Either you get the this, or you can get to this, okay? But either way, you get a carbonyl compound. So if the basically is the carbon next to the oxygen being oxidized, okay? But in case the thiol, if you want to let it react with the oxidant, it's actually sulfur is being oxidized instead of carbon. Why? That's because of sulfur is more oxyphilic than carbon. And basically sulfur can form stronger bond with oxygen, the compared to the other atoms. Okay, so that makes sulfur very oxyphilic. And if you check the electron activity on the carbon and the sulfur, they are actually same. Okay, both are 2.5. Okay, but just the sulfur is more oxyphilic. So as a result, when you oxidize thiol, it's sulfur being oxidized. So depending on the more ratios between the thiol and oxidant, you could have one oxygen on the sulfur, two oxygen on the sulfur atom, or three oxygen on the sulfur atom. So this we would just it's enough to knowing that just the oxidation happen on sulfur instead of carbon.